Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to go over gas laws. So specifically, we're going to do Boyles Law, Charles's Law, the combined gas law, and ideal gas law. Let's get started.
We are going to start with Boyle's Law. Now, Boyle's Law looks at the relationship between pressure and volume. The important thing to remember here is the amount of gas is held constant as well as the temperature. So this plot here on the left shows Boyle's original data. As pressure decreases, volume increases. Ideally, we want a linear plot. So instead of plotting pressure and volume, Boyle also plotted pressure and 1 over volume. And you can see how this has changed the relationship to a nice linear relationship. Here is the generic equation for a line, y equals mx plus b. Let's put in our variables. Our y variable is pressure. Our x is 1 over volume, and our y-intercept is 0. Our slope is simply a constant. So let's simplify this expression. And instead of slope, I have put k here to stand for just a generic constant. Let's rearrange this so that we have pressure and volume on the same side of the equation. In essence, we have solved for k, our constant. What that allows us to do is it allows us to compare an initial and a final condition. So the form of Boyle's Law that we will be working with most often is this one right here, where we're going to have initial pressure and volume and compare it to a final pressure and volume. Again, we have held temperature constant and the amount of gas constant. Let's work a problem. A sample of gas is originally at 975 millimeters of mercury and occupies 355 milliliters. If the pressure is changed to 1.95 atmospheres, what is the new volume of the gas? I'm going to make a list of everything that we know. We know the original pressure. We know the original volume. Now we have changed the pressure to 1.95 atmospheres and we're asked what the new volume is. Let's use our equation for Boyle's Law and plug in the values we have. So here are the values simply plugged in from my list. You can see we do not have unit agreement. So this pressure is measured in millimeters of mercury and this one is measured in atmospheres. We just need to make sure they're consistent. So I'm going to convert my millimeters of mercury into atmospheres. Now I have consistent units. I can solve for my V2, and my V2 is 234 milliliters. You will get the same answer if you convert your atmospheres into millimeters of mercury, just as long as everything is consistent. Now let's talk about Charles's Law. So Charles's Law looks at the relationship between volume and temperature. So pressure is being held constant and the amount of gas is being held constant. You can see that volume increases as temperature increases. But unlike Boyle's Law, we don't have a y-intercept of 0. However, if we take the data and extrapolate all the way down to the x-axis, which means we are going to cross 0 degrees Celsius, we can see we hit a temperature down here of about negative 275 Celsius. Thanks to the work of Lord Kelvin, we now know that this temperature is absolute 0. Lord Kelvin created the absolute temperature scale of Kelvin. We can see from this plot here, at some very cold temperature, volume will go to 0. Now if we plot volume versus temperature in Kelvin, we still get a nice straight line, and this line does have an intercept of 0. So we are going to treat this just like we did Boyle's Law. Here is our equation of a generic line. Let's plug in our y and x values. So our y is volume, our x is temperature, and again we have a y-intercept of 0. Our slope is a constant. So simplifying this equation, we get this equation right here. I have changed my slope to k, which just like in Boyle's Law stands for a generic constant. Let's solve for that constant. Here we go, right here. So volume over temperature equals a constant. Just like we did in Boyle's Law, where we compared an initial condition to a final condition, we do the same thing with Charles's law. Here is our final form of Charles's law. We can compare an initial volume and temperature to a final volume and temperature. Now remember that this equation came from this plot where temperature was measured in Kelvin. So we need to make sure that all our temperatures are measured in Kelvin and not Celsius or Fahrenheit. The wonderful thing is converting between Kelvin and Celsius is very simple. Here is the equation right here. So if you know your temperature in Celsius, you simply add 273.15 and that will give you your temperature in Kelvin. Now for the problems we work, we will generally drop this 0.15, but if you'd like, you may certainly keep it in. Here is our problem. A sample of gas is initially at 18 degrees Celsius and has a volume of 5.32 liters. Holding pressure constant, what is the temperature of the gas in Celsius if the volume changes to 988 milliliters? This problem did specify that pressure is held constant. However, we can also assume that the amount of gas is held constant. Let's list out what we know. We have our initial volume and our initial temperature. We have our final volume, but we do not know our final temperature. We do need to convert this Celsius into Kelvin. We also need to make sure that our volume units match. Let's do those conversions. Here we go. So now we have our temperature in Kelvin, and I converted this volume into liters. Now let's plug into Charles's law. Here is our form for Charles's law. Plugging in for V1, T1, and V2, we simply solve for T2. So our final temperature is 54 Kelvin. Now the problem did ask us for the temperature of the gas in Celsius, so we will need to convert back into Celsius from Kelvin. So our final temperature is negative 219 degrees Celsius. We use combined gas law when we want to vary pressure, volume, and temperature, but still hold the amount of gas constant. You can see it looks very much like Boyles' law and Charles's law. Let's work a problem. A gas is initially at 90,500 Pascal and negative 15 degrees Celsius. It has a volume of 0.89 liters. What will the new pressure in atmosphere be if the gas is heated to 22 degrees Celsius and compressed to 0.1 liters? We have quite a bit of information here. Let's list it out and get a little bit organized. Okay, here is our list of everything we know. We know our initial pressure, initial volume, and initial temperature. We do not know the new pressure. However, we know the new volume and the new temperature. Just like with Charles's law, our temperatures need to be converted into Kelvin. So let's do that conversion. Here we go. You can see that both of my temperatures are now in Kelvin. Now I can plug into the combined gas law. So here's my form for combined gas law, and here are all of my numbers plugged in. Solving for P2, I get 921,000 Pascal. However, my problem asks for the pressure in atmosphere, so just a simple conversion, and I get 9.1 atmospheres. That is a lot of pressure. Let's look at one more gas law. We're going to look at ideal gas law. So we have seen Boyles' law and Charles's law. One law that we did not talk about but is very similar is Avogadros Law. Yes, this is the same Avogadro that Avogadro's number is named after. All of these are equal to a constant. Now that constant is different for each law. So let's summarize these relationships in terms of volume. Here we go. For Boyles' law, volume is proportional to 1 over pressure. For Charles's law, volume is proportional to temperature. And Avogadro's law, volume is proportional to the number of moles. So we can combine the right-hand side of this equation, just like this. So volume is going to be proportional to the number of moles times the temperature over the pressure. Now, to change this proportionality into an equal sign, we just need a constant. So here I have changed it to an equal sign, and I have added this constant here, R. R is the universal gas constant. Now you may be more familiar with the ideal gas law written as this, but you can see that it's just a simple rearrangement. Now R, the universal gas constant, has several values depending on its units. So here is a table giving several values of R and their units. When you are choosing a value for R, you want to look at your units and see what matches with the pressure and volume that you have been given. However, mole and Kelvin always stays the same. Let's work a problem. What is the pressure of 0.018 moles of an ideal gas at 0.770 atmosphere, 37 degrees Celsius, and occupies 178 milliliters? Let's write down what we know. We do not know the pressure. We know the volume, we know the number of moles, we will have to determine R, and we also know the temperature. Let's determine the value for R that is best going to fit our data. Our volume is measured in milliliters. You can see here I do not have a volume in milliliters, but I have two volumes in liters. That is a very easy conversion. So I could use either value of R here. For this problem, I am going to use this value of R, which means my pressure is going to be measured in atmospheres. Here is now my list of everything I know. Notice I changed my value to liters, put my value for R in, and I also changed my temperature to Kelvin. Let's plug our numbers in. Here is our ideal gas law. Here are all our numbers plugged in. Before we solve for anything, let's make sure that our units are matching up. My volume is measured in liters. That matches there. I have moles, that will cancel. I also have Kelvin, and you can see I am left with atmospheres. Now we can solve. And I get a final pressure of 2.64 atmospheres. You can see why one of the most common mistakes here is not keeping track of your units. It is very important to write your units down and make sure they cancel properly. Let's do another ideal gas law problem, but with a little bit of a twist. Calculate the density of helium if it has a pressure of 891 torr and the temperature of the sample is at 18 degrees Celsius. So let me show you a rearrangement of the ideal gas law to give density. Here it is right here. So density is simply the pressure times the molar mass of the gas. Here is our universal gas constant and temperature. We will need to choose an appropriate value for R. Because we are given pressure and torr, I am going to choose this value for R because it also has pressure and torr. Let's plug our numbers in. Here is my pressure. Here is my molar mass of helium because the problem specifically said I have helium. My value for R that I chose, and my temperature. Notice I converted to Kelvin. Let's make sure units cancel. My torr cancels, my moles cancel, and my Kelvin cancels. So the units I am left with are grams per liter. Let's go ahead and work through this calculation. So I get a density of 0.197 grams per liter. Again, these are the units that I was left with from up here. Density very often is measured in grams per milliliter. So let's simply convert this liters into milliliters. Here's my conversion factor, and so for my final answer, I get 1.97 times 10 to the negative fourth grams per milliliter. Again, you can see this problem is all about the units.
The most common mistake that students make when working gas law problems is forgetting to convert into Kelvin. So make sure you get those temperatures in Kelvin. Thanks so much for watching.